Okay. All right, so I think I'm live on YouTube, so let me get started. Okay, so let me also share my screen before I forget to do that too. And let me go to the PowerPoint. And I recall that the last thing we discussed in this chapter had to do with the relationship between kinetic energy and temperature and pressure and other functions or other variables. And the next topic that we're going to talk about is molecular speeds, all right? So we know that the kinetic molecular theory talks about the fact that the particles of a gas or the molecules of a gas are always moving. And as you can imagine, it's a pretty random situation where gases, gas particles are all moving at different speeds, right? So what we use to calculate the average speed is what is called the root mean squared speed, all right? And which by definition is the square root of the average of the squares of the molecular speeds. So let me try to explain what we mean by that. So let me go to my writing pad here. So the root mean squared speed, which is symbolized using this symbol here, URMS squared, is equal to the speed squared of gas one, or molecule one, I should say, plus the square of the speed of molecule two, plus the square of the speed of molecule three, and so on until you get to the nth molecule. And then you divide all of that by the total number of molecules. So basically, the root mean squared speed would be, let me just take this out here, would be the square root of all of this right here, all right? So whenever you hear the term root mean squared speed, we're talking about this here that I just wrote over here, right? It's basically the sum of the squares of the speeds of the individual molecules divided by the total number of molecules, all right? And that is used as a measure of basically the average speeds of the molecules, because as we said before, not all molecules will be traveling at the same speed. Some will be higher, some will be lower, some would be in between. So therefore, that's what we use to calculate the average speed, all right? Now it turns out that the root mean squared speed, which I just mentioned, can be shown to be equal to the square root of 3RT over M. R, of course, is a molar gas constant, T is the temperature in Kelvin, and M is the molar mass. But you have to be careful when you're using this equation with respect to the units. So let me go back to my writing pad here and explain what I mean by that. So the equation is the root mean squared speed is equal to the square root of 3RT over M. Now for this equation, the R that you're going to use here is not the one that we have been using all along in this chapter, which was 0.0821, right? The R that you're going to be using here is going to be 8.31 joules per mole second, all right? Another thing you need to be aware of is that the molar mass, right? The units of the molar mass that you're going to use in this equation must be expressed in kilograms per mole, all right? So normally you would use the molar mass. When you calculate it, you get it in grams per mole. Then what you have to do next is divide by 1,000 to convert it to kilograms per mole. And the reason why those two changes are important, I'm going to show you here. Now what I'm going to do is just show you the result of just using the units in this equation, right? So the units of R would be joules per mole second, and the units of T would be Kelvin. I'm sorry, this should be mole kelvins. I'm sorry, this should be mole Kelvin, not mole second, mole Kelvin. All right. The T, as I said before, would be in Kelvin, and then the molar mass units would be kilograms per mole. Okay, now here is something that you may or may not know. The joule unit is the same thing as kilograms meter squared over second squared, all right? So if we replace the joule unit here with this collection of units here, if we plug this in here, this is what we're going to end up with. The square root of kilogram squared, meter squared over second squared times over mole Kelvin times Kelvin divided by kilograms per mole, all right? So if you put those units into this formula here, you're going to see some cancellation taking place. For example, the Kelvin here and here will cancel out, the mole units will cancel out here, and the kilograms will cancel out here and here. So what you'll be left with is the square root of meter squared over second squared, which means that the units of molecular speeds will be resulting in being meters per second, all right? So I'm just going through all of this. I'm just going through all of this to show you why is it that the R value that you're going to be using is this, and the units of molar mass, whatever the molar mass you calculate, must be expressed in kilograms per mole, because once you do those, once you take those into account, then the units for molecular speeds will be meters per second. Okay, so with that out of the way, as stated here, the speeds are usually quite high, as you can imagine, on the order of 1,000 meters per second. And one important thing I want to point out about this relationship between the root mean squared speed and the temperature and the molar mass, you're going to see that, for one, the higher the temperature, the higher would be the root mean squared speed, which makes sense. The higher the temperature, the more energy you're imparting to the molecules, and therefore the molecules will be moving faster, all right? So no mystery there. The other thing I want to point out here is the relationship between the root mean squared speed and the molar mass. And you can see clearly, based on this equation, the molar mass, as it gets greater, the root mean squared speed is smaller if the temperature is a constant, right? So basically, you can make comparisons between two gases. And if they're at the same temperature, you can actually predict which one would have a higher root mean squared speed. So for example, if you were comparing, let's say, let me go back to my writing pad here. So if you were comparing, let's say, nitrogen monoxide to nitrogen dioxide, right? Well, this one has a larger molar mass. So the molar mass here, molar mass, or let me just use M here, is larger than the M here. So the M for NO2 is larger than the M for NO, which means that the root mean squared speed for NO would be greater than the root mean squared speed for NO2, because the nitrogen monoxide has a lower mass compared to the nitrogen dioxide, all right? Okay, what's next? All right, so another thing I want to point out here, and I made reference to it earlier actually, is the relationship between the temperature and the root mean squared speed. So as I said before, the higher the temperature, the greater would be the root mean squared speed. And of course, as I said before, the molar mass, of course, the lower the molar mass, the greater would be the root mean squared speed. So let's deal with that one first. Now, I want to explain what we're looking at here. We're looking at two graphs. In both cases, we're plotting the relative number of molecules versus the root mean squared speed, all right? Or just the speed of the molecule. So if you focus on the one here on the left, we have three plots, one for oxygen, which is represented by the pink line, one for methane. I'm not sure what color line this is. It looks blue or green, I don't know. And then the hydrogen, the plot for the hydrogen is shown here, all right? Now, in terms of the graph, the root mean squared speed can be determined by looking at where the apex is of the particular plot and dropping a vertical line, and where it cuts the x-axis, that would be the root mean squared speed, all right? So in the case of oxygen, the root mean squared speed here looks like, okay, so this looks like about 500. So I would say somewhere about 400, all right? If you look at methane, you drop a line down here. This looks like, I would say about 700. Whoops, Sorry about that. And then finally, in the case of hydrogen, this is easy because this looks like 1500. So you'll notice as you go from oxygen to methane to hydrogen, you see that the root mean squared speed increases. And that makes sense because oxygen has a molar mass of 32, so it would be the heaviest. Methane has a molar mass of about 16, which would be next in line in terms of mass. And then the lightest molecule here is hydrogen, which has a molar mass of about 2. So therefore, this falls in line with what we would have predicted from the equation I showed you. Basically, as the molar mass decreases, the root mean squared speed of the molecules increases at the same temperature, which in this case is 273. Now, let's focus our attention on the graph on the right. It's the same gas, oxygen, so the molar mass is not changed. What is changing is the temperature. So we're going from 273 to 1000 to 2000. So at 273, as we said before, the molar mass, the root mean squared speed of oxygen is about 400. At 1000, it's just about 500, I would say about 600 meters per second. And then here, for 2000 Kelvin, it is just shy of 1500. So I would say probably about 1450, right? So obviously what we see here is that as the temperature increases, the root mean squared speed increases, again, as predicted by the equation I showed you earlier, all right? Okay.
Oh, the way the graph looks, does this also mean that as the temperature increases, the variance in how fast molecules are traveling also increases?
Well, yeah, exactly, the speeds. Generally speaking, the speeds of all the molecules, well, I wouldn't say all, but most of the molecules, their speeds would increase. So that's why the average speed increases as the temperature increases.
Yeah, just on the graph, it shows that there are some molecules that are moving quite fast, 3,000 or 4,000,
right?
and some that are,
Exactly.
it's more spread out.
Right, exactly. It's more spread out, and you'll always have that distribution. That's another thing you'll notice too. As the temperature increases, the distribution, what's the word I'm looking for? Distribution, width, I think, or range, maybe that's a better term, increases.
Yeah.
Right. You have molecules that are, well, you have a few molecules that are moving very slow, right? And then you see as you follow this here, it goes up to a maximum and falls off. So what we pay attention to in most cases is the average, the root mean squared speed, which is represented by the peak of the curve. But you're right, there's always going to be a distribution. You're not going to have a situation where all the molecules are moving at the same speed. You're just going to have a distribution of molecular speeds at every temperature, pretty much. All right.
Okay. All right.
Okay. So now we're going to get into a discussion of two terms, diffusion and effusion. Now we won't be spending much time on diffusion. In fact, I think there's only one slide here which deals with this. So what is diffusion? This is a process by which one substance mixes with one or more other substances as a result of the translational motion of molecules. All right, so basically what we're talking about when it comes to diffusion is how one substance spreads within another substance or more than one substance, all right? Now, it was what's the word I'm looking for? Scientists or chemists were thinking about the fact that, okay, since we know the relationship between the root mean squared speed of molecules and other factors such as temperature and molar mass, maybe that could serve as a model for what happens in diffusion. However, that's not to be because as stated here in the second point, diffusion of gases is much slower than would be predicted by the molecular speeds based on the equation I showed you. And the reason for that is due to the frequent collision between the molecules of the substance that is spreading through and hitting the other substances, all right, or the other molecules. So therefore, the equation that I showed you, root mean squared speed is equal to the square root of 3RT over m. That equation would not serve as a useful model for describing diffusion as a process. On the other hand, effusion, oh, I'm sorry, I'm skipping one slide here. Before we get to effusion, I want to point out an interesting exercise here. Now, what do we have here? We have two bottles. one containing hydrochloric acid concentrated, and the other one containing concentrated ammonium hydroxide, all right? Now, if you leave these two bottles unopened and next to each other, eventually what you're going to see is a smoky substance being formed at the mouth of the bottle containing the hydrochloric acid. Now, that substance, let me go to my writing pad here again. That substance is formed as a result of hydrogen chloride gas from the hydrochloric acid reacting with ammonia gas from the ammonium hydroxide to form ammonium chloride, all right, which is a solid. Whoops. All right. So the smoky substance that you see at the mouth of the hydrochloric acid is due to the formation of the ammonium chloride as a result of the reaction of these two gases coming from each of the concentrated solutions. Now, here's my question to you, and I want you to think about this carefully. Why is it that the ammonium chloride is formed at the mouth of the hydrochloric acid and not anywhere near the mouth of the ammonium hydroxide?
I think I've guessed it. Is the hydrochloric acid, what's the word? More massive than the ammonium hydroxide?
Okay, and therefore?
It doesn't diffuse as fast, and so the ammonium hydroxide gets to the neck of the hydrochloric acid bottle first.
Yeah, you're pretty much right. The hydrochloric acid molecule is heavier compared to the ammonia molecule. The hydrogen chloride molecule is about 36.5 AMU, while the ammonia is about 17, so almost 2 times, or actually greater than 2 times, right? So therefore, because the hydrogen chloride molecule does not travel as fast as the ammonia molecule, they will meet each other closer to the bottle containing the hydrochloric acid. And that's why you see the ammonium chloride formed here. I remember when I was in high school, my high school chemistry teacher did a little experiment. Let me try to describe it for you. He had a tube. Please forgive my lack of artistic skills, but I'll try to explain what's happening here. He had a tube, right? And one end of the tube was plugged with cotton containing concentrated hydrochloric acid, and the other end of the tube is plugged with cotton, which is soaked with concentrated ammonium hydroxide. And then when you sit for a while, what you'll notice is that you're going to see a ring, a white ring, formed closer to the cotton with the hydrochloric acid, and that would be the ammonium chloride, right? And the same argument applies. The hydrochloric acid molecule travels slower compared to the ammonia, so therefore when they meet, they will meet somewhere nearer to where the hydrochloric acid soaked cotton is located. So that's another demonstration of the fact that you can show that the hydrogen chloride gas molecules move slower compared to the ammonia molecules. Okay, any questions? Yeah, and it happened in no time, if I remember correctly. Like, he just, plug them, and then we just sat there and watch it, and you see the solid form closer to the HCl. Okay, so, okay, what am I doing here? Oh, let me go back to PowerPoint. Okay, so let's talk about effusion. Now, effusion is a better process in terms of using the equation that we talked about to model it. Now, effusion, by definition, is a process in which a gas escapes from its container through a tiny hole or orifice into a vacuum, right? So if you have your gas, and in this case, you have a mixture of gases, right, in a container, you have a very small hole, and the gas particles are escaping from the hole into vacuum. So there's no other substance outside here. So therefore, we're talking about effusion in this case and not diffusion. And what you're going to notice is that in this particular situation, the heavier molecules will move more slowly, and therefore the rate of them escaping through the hole will be lower compared to the lighter molecules, all right? So the red spheres represent the lighter molecules, the blue spheres represent the heavier molecules, so therefore you'll notice you have more red spheres escaping compared to the blue spheres, which means that in here, you're going to have more of the heavier molecules remaining, all right? Now let's look at the math behind this, right? So if you were to compare two gases, gas 1 and gas 2, right? So we can write down separate equations for their rates of effusion. So the rate here for gas 1 is equal to the square root of 3RT over M1, and for rate for gas 2 is equal to square root of 3RT over M2 for gas 2. And if we do the cancellations of the 3RTs here, then you end up with this equation. So therefore, what this equation is saying is that the rate of the effusion of a gas is inversely proportional to the square root of the molar mass. You'll note that rate for gas 1 is here, and the molar mass of gas 1 is down here, and rate for gas 2 is here, and the molar mass of gas 2 is up here. So there's an inverse square root relationship between the rate of effusion of a gas and its molar mass. And that's basically what we call Graham's law of effusion, right? This is a mathematical expression of it. In terms of how you express this law in words, this is the way you express it. At a fixed temperature, the rates of effusion of gas molecules are inversely proportional to the square root of their molar masses, all right? So, and again, that makes sense. The heavier the molecule, the lower the rate of effusion, and vice versa. Okay, so let's look at an example, all right? So this question says, if compared under the same conditions, how much faster than helium does hydrogen effuse through a tiny hole? All right, so let me go back to my, okay, so basically, what the question is asking for is the ratio of the effusion of, let me see this again, on how much faster than helium does, okay, so we're looking at the ratio between hydrogen and helium in terms of the rate of effusion. So the way I'm going to write it is that the rate of effusion of H2 divided by rate of effusion of He, all right? This is what the question is basically asking for, all right? So first thing I'll write down is the relationship mathematically with respect to their relationship to their molar masses. So that means that this ratio here would be equal to the molar mass of helium divided by the molar mass of H2, all right? So what we have to do, of course, is go to the periodic table and look up the molar masses of the different elements. And if I remember correctly, the molar mass of helium is 4.008 AMU, or divided by the molar mass of hydrogen, which is H2, which is 2.016 AMU, and we find the square root of that. So go to my trusty calculator here, 4.008 divided by 2.016. So we find the square root of that. And according to my calculations, when rounded off to 4 sig figs, this would be equal to 1.410, all right? So that is the ratio of H2 rate over the rate of effusion for He. So therefore, another way of stating this is that the rate of effusion of H2 is equal to 1.410 times the rate of effusion of He. So the answer to the question is H2 effuses 1.410 times faster than helium. And that would be the answer. All right? Any for this example?
I thought in this when we were talking about the mean average speed, we use kilograms instead of the normal measurement of molar mass?
Oh, okay. So, okay, I'm glad you raised that question because you only use kilograms per mole if you're using this equation. Rate, I'm sorry, root mean square speed is equal to the square root of 3 RT, whoops. Okay, what the hell is going on? Oh, I hate when this happens. Okay, I don't know why. I don't know what I'm doing wrong here. Well, let me do that. No, that don't work. Okay, I don't know what's going on here. Let me do it over here. Root mean square speed is equal to 3 RT over M, and you find the square root. You only use R equals to 8.31 joules per mole Kelvin, and this is expressed in kilograms per mole if you're going to be using this equation, right? In this case, it wouldn't make any difference because the units are going to cancel out here and here anyway. All right.
Okay.
So you only use what I mentioned before, the units, kilograms per mole mass and 8.31 joules per mole Kelvin when you're using this equation. So in fact, let me do an example using that equation so you see what I'm talking about. Let me clear this here because this is annoying me. Okay. Random example I'm going to use here. Let's say you're asked for the URMS speed for carbon dioxide. Shoot. This thing is going to make me cuss. Okay. You know what? Let me use another writing software. Let me use this one here. Let me see if it works. Okay, it works. Okay. What was I about to say? Oh, the root mean squared speed of carbon dioxide at 25 degrees, right? So your task is to calculate it. Then you just use the equation URMS is equal to the square root of 3 times 8.31 joules per mole Kelvin times the temperature, which must be expressed in Kelvin, 298 Kelvin, divided by the molar mass of carbon dioxide. Now, I know that the molar mass of carbon dioxide is 44.01 grams per mole, right? But you have to convert that to kilograms per mole. So that means that you have to multiply by 1 kilogram up here and 1,000 grams down here, all right? And that's basically it, all right? So let me do this on my calculator. 3 times 8.31 times 298 divided by 0.0441, then find the square root. Okay, so according to my calculations, the root mean squared speed of carbon dioxide at 25 degrees Celsius, how many sig figs? 3 sig figs, is equal to 410 meters per second. All right, and that's basically how you do that.
Oh, okay, that makes sense.
That clarifies things for you. You only use the units that I mentioned when you're calculating directly based on the temperature and the molar mass. Now, in the case of Henry's law, which I guess I erased it. In the case of Henry's law, it would make a difference because the units will cancel out when you do the division. So that's basically how that is done. Let me go back to here. Okay, so this is the example we just did. Here's another example. Now, this one you have to be a bit more careful about because in this case, the question says that 1% of a measured amount of argon escapes through a tiny hole in 77.3 seconds. So they did not give you the rate. They gave you the time of effusion. And if you understand the relationship between rate and time, you'll know that there's an inverse relationship, right? The faster the rate of a process, the shorter the time it takes for the process to be done, right? And vice versa, all right? So it says here, continuing, 1% of the same amount of an unknown gas escapes under the same conditions at 97.6 seconds. So the question is asking for you to calculate the molar mass of the unknown gas. All right, so let me go to this one. Okay, so according to the question, the time of effusion of argon is equal to 77.3 seconds, and the time of effusion of the unknown gas is equal to 97.6 seconds, all right? Just thought I should write those two numbers down so I can have them to look at. Now, as I said before, there's an inverse relationship between the time of effusion and the rate, right? So time of effusion will be proportional to 1 over the rate of effusion, all right? So if I were to write this down, time of effusion of argon divided by time of effusion of the gas, unknown gas, that would be equal to the rate of effusion of the unknown gas divided by the rate of effusion of argon. And based on Graham's law, this would be equal to the square root of the molar mass of argon divided by the molar mass of the unknown gas, all right? So basically, what the question is asking for is the molar mass of the gas. Now we know these two numbers, these two values here and here, and we can look up the molar mass of argon here. So basically, we have to do some algebra to solve for mg. Now, from your previous algebra experience, you should know that in order to get rid of the square root sign, we simply square both sides. So if we square both sides, you're going to end up with the time of effusion of argon divided by the time of effusion of the gas squared will be equal to the molar mass of argon divided by the molar mass of the unknown gas, all right? So if we solve for the molar mass of the unknown gas, do this down here, molar mass of the unknown gas would be equal to the molar mass of argon times time of effusion of the unknown gas divided by time of effusion of argon, and all of this to be squared. And all we have to do now is plug in the numbers. Let me look up the molar mass of argon. So according to my periodic table, the molar mass of argon is 39.95 grams per mole, multiplied by the time of effusion of the unknown gas, which is 97.6 seconds, 97.6 seconds, and that for argon is 77.3 seconds. The second units will cancel out. So let me do my calculation here. 39, oh, very important. How could I forget? Squared. Okay. So let me do what's within the parentheses first. 97.6 divided by 77.3. Then I square it, and then I multiply by 39.95. And to round this off to how many sig figs? 3 sig figs, the answer becomes 63.7 grams per mole, all right? And that's basically how that is done, which makes sense because the time of effusion of the unknown gas is longer, which means that the rate is lower, which means that the unknown gas molecule must be heavier, all right? So that's basically how that works out. Okay, any questions about this particular example? Any questions? Any questions?
Don't believe so.
Okay, so let's move along to a discussion of real gases. Now, all along in this chapter, we were assuming that the gases that we were dealing with were ideal gases. So what do we mean by ideal gases? Ideal gases are gases that basically obey the ideal gas law. That's one way of defining it. But there are some aspects of the gas properties at the microscopic level which makes a gas ideal. And the two main ones are, one, there are no intermolecular forces between the gas particles. And two, the size of the particles are much smaller, infinitesimally smaller compared to the sizes of the container that they're in. In other words, the size of the particles are effectively zero compared to the container, all right? So those are the two basic requirements at the microscopic level for an ideal gas, right? Of course, we know that real gases are not ideal because, for one, in the case of real gases, we have intermolecular forces that do exist between the gas particles. And two, the gas particles are not effectively zero. They're small, but not zero, right? So therefore, we have, those differences between the real gases and ideal gases, all right? Now, even though that is true, we can actually alter conditions such that the real gases behave more and more like an ideal gas, right? And what are those conditions? Basically, high temperature and low pressure, right? So if you increase the temperature of the gas and at the same time lower the pressure of the gas, then that real gas will become more and more like an ideal gas, all right? And there's a graph which kind of demonstrates this. Let me try to recreate this graph again using my writing pad here. If I remember correctly, I need to look up this graph and post it so you guys can see. This graph is a plot of, if I remember correctly, PV over RT. Is it PV over RT? I think it's PV over RT, if I remember correctly, right? I'm sorry, PV over NT, right, which is equal to R, right? And here we have the temperature plotted. Now, for an ideal gas, this would be the plot, right? Because we know that R is a constant, so therefore PV over NT is going to be one straight line like this. Doesn't matter what the temperature is, but this would be the plot for the ideal gas, all right? Now for real gas, let me use a different, can I use a different color? Let me see. Okay, let me use that color here. So for real gas, the plot will look something like this. All right. Oh, I just remembered something. This should be pressure, not temperature. My bad. Okay, so this is for a real gas, all right? And what you'll find is that as you increase the temperature, right? In this case, let me just make sure this is looking like what it should be. As you increase the pressure, as you increase the temperature of the gas, what you'll find is that the plot changes like this, right? So, and then you increase the temperature again, and it changes like this. And if you increase the temperature again, so you'll notice what happens is that the plot for the real gas flattens and become more and more like the plot for the ideal gas, all right? So this demonstrates what happens as you increase the temperature. So let me just write here, increasing temperature. As you increase the temperature, the plot more and more resembles what you'd expect for an ideal gas, and that's for a real gas.
Oh,
I
see.
Yeah, I'm going to see if I can find that that plot so that you can see, because of course that plot is much better than the one that I'm showing you right now. But basically what I'm trying to show you is that the real gas will behave more and more like an ideal gas as you increase the temperature, all right? Okay, any questions?
No, but that makes more sense to me now. If it's at a higher temperature, then it's going too fast for intermolecular forces to affect it.
Exactly.
And if it's at low pressure, then
Mhm.
it's a lower fraction of the total volume.
Exactly. And in fact, what I'm about to show you next is speaking towards the first point you made. Let me show you this here. So this is showing you the difference between an ideal gas and a real gas in terms of the pressure exerted. As we said before, in the case of an ideal gas, there are no intermolecular forces between the particles, right? So therefore, if you focus on one particle hitting the wall of the container, it will do so without being affected by any of the surrounding molecules, right? On the other hand, in the case of a real gas, because of the intermolecular forces between this particle and the surrounding ones, they'll have a greater pull on that particle, and therefore it will not be as free to hit the wall of the container with the same force as it would have been in the case of an ideal gas. So that explains why the pressure exerted by an ideal gas would be greater compared to the pressure exerted by a real gas. It has to do with the fact that in the case of an ideal gas, there are no intermolecular forces hindering it from hitting the wall of the container, whereas in the case of a real gas, that would be the case. All right. So that speaks to the first point you made a while ago. All right. Okay. Now, this begs a question. So can we come up with an equation for a real gas? We know what the equation for the ideal gas is. And a Dutch scientist by the name of Van der Waal did some theoretical work, and he came up with an equation which is basically a modification of the equation for the ideal gas. And that equation that he came up with describes the behavior of real gases, right? So this is Van der Waals equation, right? And if you compare it to the ideal gas equation, you can see the modification. So this is the ideal gas equation up here. This is the Van der Waals equation here. And you see that there's some new terms indicated or included, such as this term right here and this term right here to get your Van der Waals equation. Now, these modifications include certain constants. You have A, which is indicated here, which is a term which is related to the intermolecular force strength. All right. And then you have B, which is related to the volume of the gas molecules, which is placed right here. All right. So the terms A and B are based on experimental constants, which are basically unique for different gases. And just to give you an idea of what we're talking about, these are just a sample of gases and their A values and their B values. All right. You don't need to know this. I mean, you know, you don't need to memorize the Van der Waals equation, but of course you need to understand why the Van der Waals equation was discovered and derived. And it just basically comes down to the difference between the behavior of ideal gases and real gases. All right. And that's basically the end of chapter 5. So if there are no questions about what we just talked about, we're going to move on to chapter 6, which deals with the area of chemistry known as thermochemistry. Okay, so what is thermochemistry? Thermochemistry, as the name suggests, basically involves looking at energy changes occurring in a chemical reaction, all right? So in order for us to appreciate what is happening as far as energy changes are concerned, we have to be introduced to certain terms, you know, such as energy, temperature, and the different types of energy and so on. So that's what we're gonna do right now. So what is energy? Energy by definition is the capacity to do work, which begs the question, what is work? Well, work is what takes place when you apply force to an object and the object moves, right? So if I push on something like a door and the door moves, then I'm doing work on the door, right? Now, if I push on something and it doesn't move, that means I'm not doing work, because in order for work to be done, the object has to move when you apply the force, all right? So as we said before, energy is the capacity to do work, and work is said to be done when an object moves upon application of a force. Now, there are two basic types of energy. You have potential energy, which is the energy that an object has by virtue of its composition or position. And then you have kinetic energy, which is the energy an object has by virtue of the fact that it's moving. All right, so those are pretty much all forms of energy can fall under one or the other category. All right, so this is basically a comparison between kinetic energy and potential energy side by side. So as we said before, potential energy is the energy an object has by virtue of its position or composition, and kinetic energy is the energy an object has by virtue of the fact that it's moving. And we can calculate using equations both types of energy. So this is the formula for potential energy. If you have an object elevated above ground level, then this is what that means is that the object has an energy relative to the ground level, and it can be calculated using this equation. If you have done physics, or if you're about to do physics, you're going to meet this equation. Mass times g times h, mass is in kilograms. G is called the acceleration due to gravity, which is a constant, which is 9.81 meters per second squared. And h is the height above ground level that the object is located. And then over here, we have the formula for calculating kinetic energy, which is half mv squared, where m is the mass in kilograms, and v is the velocity in meters per second, all right? And you'll notice that as a result of using either equation, you'll notice that the final units will be kilograms meters squared per second squared, which is the same thing as the joule unit. I think I mentioned this earlier when we were talking about the relationship between root mean squared speed and molar mass and so on. So this is a joule unit. The joule unit is the same thing as kilograms meters squared per second squared. Same result here as you would have here, regardless of which equation you use to calculate the energy, either potential or kinetic. Okay, as I said before, work is said to be done when force is applied to an object and the object moves a distance, right? So the equation for calculating work is force times distance, and has the same unit of energy, which is joule. And in this case, the unit of force will be newtons and the unit of distance will be meters. Now, whenever you have objects colliding, right? Moving objects colliding, and they hit each other and then they bounce off. The collisions are not always going to be, in fact, in the real world, it's not going to be perfectly elastic. What that means is that you won't have the direct transfer of energy from one object to the other. You might have some energy loss due to heat, sound, etc., right? And that can be seen, for example, if you take a tennis ball, right, and you lift it above the ground, and then you release it and it drops. And we all know from everyday experience, when it drops and hits the ground, it bounces up. I'm sorry. It bounces up, but you'll notice that it will never bounce up to the same height from which it falls from the beginning, right? And then it bounces again, and the maximum height here is less than what it was before, and that continues, right? And that's because the energy is not elastic. You have energy transfer as the ball hits the ground. For example, the sound that you hear when the ball hits the ground, that's of course a form of energy. So therefore some energy will be lost as a result of that. The ball might get warmer. So therefore some heat energy is lost as a result as well. So therefore that explains why with each bounce, the height of the bounce becomes lower and lower, all right? So that's just a demonstration of the fact that the collisions of particles are not elastic. Okay, so as we said before, thermochemistry is that area of chemistry which study energy changes that occur during chemical reactions. And when we're talking about thermochemistry or thermodynamics, which we'll talk about in general chemistry 2, for those of you who have to do Chem 2, you need to make a distinction between what we call the system and the surrounding. Now, the system in this context is a particular area of interest, all right? So for example, the system could be regarded as a reaction in a test tube or, you know, a reaction in some vessel, right? That is what we call the system, okay? everything outside of the system, which is a part of the universe, is called the surroundings, right? And in thermochemistry, we are focused on the exchange that takes place between the system and the rest of the universe, the surrounding, especially when it comes to heat flow, right? So we're concerned with whether or not a process takes place in a system, and as a result, heat is either lost by the system or heat is absorbed by the system from the surroundings. So that's basically what we are concerned with in this area of thermochemistry, all right? So basically the system plus the surroundings would be equal to the universe. All right, so when it comes to system, there are three types of systems. You have the open system, the closed system, and the isolated system. So let's talk about the difference between these three. The open system is one that allows for the exchange of energy and matter between it and the surroundings, right? So that is what happens in the case of an open system. A closed system is the one that only allows energy exchange between system and surroundings. In other words, matter is not exchanged between the system and surroundings when it comes to a closed system. And then finally, in the case of an isolated system, there is no exchange of matter or energy between the system and the surroundings, all right? So it's very important that you understand the difference between these three types of systems. Okay, so let's talk about internal energy. The internal energy is the total energy that exists within the system. Some of it will be kinetic and the rest will be potential. So if you look at things at the microscopic level, you'll see that there are three types of molecular motion which would fall under the kinetic category when it comes to energy. You have translational motion. So when we're talking about translational motion, we're talking about the particles moving along straight lines. And then we have rotational motion, where we have the particles rotating around a certain axis. And then we have vibrational motion. And this is true, excuse me, in particular for molecules, where you have atoms vibrating around a bond, as you can see demonstrated in these diagrams right here. So these are the three types of molecular motion that's associated with kinetic energy. And then we have, as far as potential energy is concerned, you can have two types, one which involves intramolecular interactions. So for example, the energy of a bond, the bond may be covalent or ionic, which is attraction between basically charges that are opposite. So that's one form. And then the other form is through intermolecular forces, which are forces that exist between molecules. These are forces we're going to learn about later on when it comes to van der Waals forces, hydrogen bonds, and so on and so forth. So we're going to talk about those later on. But those are basically the two types of potential energy forces. Okay, another term that I need to discuss with you guys is the term heat. Heat is the energy transfer resulting from thermal differences between system and surroundings. In other words, if there's a temperature difference between the system and surroundings, then you're going to have the heat transfer from the hotter object or the object with the higher temperature to the object with the lower temperature, all right? So as stated here, there's a spontaneous flow of heat from higher temperature to lower temperature, as you can see represented by this diagram here. So basically the red object is hot, the purple object is cooler, and the heat flow will continue from the hotter object to the cooler object until both objects are at the same temperature, and we call that a state of dynamic equilibrium, which will become important when we come to looking at solving certain problems. We're going to see some examples shortly. Okay, so looking at things at the microscopic level, basically this is what happens when you have heat transfer. So this is purely hypothetical, of course, but it explains what we just talked about. So basically we have argon here on this side of a hypothetical thin wall. We have nitrogen molecules here. We have we have argon here, which is a part of the system. Nitrogen is a part of the surroundings. And you have the heat flow going from the argon from the system to the surroundings, primarily because the particles here would be of a higher energy, all right? So that's what happens when you have heat transfer. Basically, it's not a matter of the particles themselves transferring, it's the energy that they would convey when the argon atoms hit the walls of hit the hypothetical thin wall, and the nitrogen molecules picks up that energy and start moving at a faster rate. And as I said before, this heat flow will continue until the system and surroundings are at the same temperature. Okay, some more things about work we need to talk about. Work, as we said before, is what happens when force is applied to an object and the object moves. But another way of looking at it, it's a form of energy transfer between a system and the surroundings, right? Now, please recall that PV, let me go to my, let me try this and see this will work. Remember that PV is equal to nRT, right? Now it turns out, if you look at the units here, this is moles, this is R is joules per mole Kelvin, and T is in Kelvin, right? So basically the product of PV gives you a value which would be expressed in joules. So basically what we're saying is that PV, P times V would be equal to energy or work, all right? So let me go back to the PowerPoint here. Okay, so that's why it says here PV is equal to energy, all right? So we can apply this to this particular system right here. So imagine, if you will, you have a gas trapped in this vessel right here. You have a movable plate right here, which is not affected by friction. So you can easily slide the plate down and up. And basically, if the gas undergoes, let's say, an expansion from here to here, right? What is happening is that basically the gas will be acting against the surroundings. Now remember, we're talking about this being the system right here. This is the area of interest that is a part of the universe, and the rest of the universe would be the surroundings. So basically when a gas expands from its initial volume to the final volume, it's expanding against the surrounding. In other words, it is doing work against the surrounding. The gas is doing work against the surrounding, which means that the gas will be losing energy as it expands, right? On the other hand, if you go the other direction, where the gas volume is being reduced, then basically the surroundings is doing work on the gas, and therefore the gas will be gaining more energy, all right? So expansion is where the gas is doing work against the surroundings, and compression is where the surroundings is doing work against the gas, right? In expansion, the gas is going to be losing energy. In compression, the gas will be gaining energy. All right, so how do we calculate work based on this equation according to the system here? Well, work will be calculated using this equation here. Work is equal to minus P times the change in volume. I don't know if you're familiar with this symbol here. It's a symbol that is used a lot in calculus. Basically delta, this is the Greek letter delta. Delta in calculus means change. So basically delta V means change in volume, all right? So W is equal to minus P times delta V, right? Now, it's very important that you pay attention to the sign conventions when it comes to the system doing work or work is being done on the system. If the system is doing work, right, what that means is that the system will lose energy, right? And therefore, what that means is that the actual value of W is going to be negative, all right? So if the system is doing work against the surroundings, the system will be losing energy, and therefore the sign, the energy change sign would be negative, all right? On the other hand, if work is done on the system, I'm sorry. So this is basically, again, reiterating what I just said. Expansion means the system is doing work, and that is what we were talking about going from here to here, right? Where the initial volume is smaller compared to the final volume, all right? So basically work is done by the system, and therefore, as far as the system is concerned, it is losing energy as a result of that, all right? On the other hand, if work is done on the system, then that means that the system, as far as the system is concerned, work will be positive. And that is what happens as you go from here to here, right? As you go from here to here, compression is taking place, which means that the surroundings is doing work on the system, which results in a smaller volume. And therefore, as far as the system is concerned, the work will be positive. All right. Okay. Let me see here. All right. I think this may be the last topic we're going to talk about, the states of a system. Now, when we're talking about state, before this topic, I'm quite sure if I ask you about the states of a substance or states of matter, you'll tell me solid, liquid, and gas, right? Those are the three states of matter, which is true to a certain extent. But when it comes to thermochemistry and thermodynamics, the term state is a bit more complicated. As you can see from this definition, the state of a system refers to its exact condition determined by the kinds and amounts of matter present, the structure of this matter at the molecular level, and the prevailing pressure and temperature. So basically, the state of a system is referring to more than just whether or not we're dealing with a solid, liquid, or gas. It is determined by a lot of other things in terms of, well, including the amounts of substance present, the type of structure at the molecular level, and of course, conditions such as pressure and temperature. So let me explain what I mean further by using some example of different states. Let me go back to my writing pad here again. Okay, so let's say I have hydrogen gas at 0 degrees Celsius. And I increase the temperature of the same gas to 25 degrees Celsius, right? Well, these are two different states. This is state 1 and state 2. Why are they two different states? Simply because the temperature is different, right? Even though they're both gases, right? But because the temperature is different, the hydrogen here is in a different state compared to the initial state here, all right? Let me give another example. Suppose you're given CO2 gas at 1 atmosphere, and all of a sudden you reduce the pressure to CO2 gas at 0.5 atmospheres. Again, these are two different states. This is state 1 and state 2. All right, why? Again, in this case, the pressures are different. Again, it doesn't matter if it's still at the gaseous phase, but the state is different simply because the pressure is different. Let me give another example. Let's say you have iron, solid, 10 grams, and then all of a sudden you just add some more to get iron, solid, 20 grams. Again, we're talking about different states because the masses are different, all right? So, you know, I'm just giving you these examples just to demonstrate what we mean by state when it comes to thermochemistry, all right? Okay, so going back to here, the state, okay, hold on 1 minute. Okay, so let's talk about the internal energy. So the internal energy, we talked about it before, and it is of course a function of the state of the system. So basically any changes in pressure, temperature, structure, whatever will change the internal energy. Which brings us to another term which I need to introduce to you, and this is called state function. A state function is a property that has a unique value that depends only on the present state of the system and not on how the system or the state was reached, nor on the history of the system, all right? So we're going to learn about different state functions. One of them we have actually met before, which is the internal energy, right? So just using that as an example, the internal energy does not depend on the present state of the system and not on how the state was reached, right? So if you have, let's say, state 1, right, and you have a certain internal energy value, it doesn't matter if you went through a more complicated route to get to state 2 or a simpler route to get to state 2, the energy, internal energy at state 2 will be independent of the route that you take, all right? So the difference in the internal energy would be the same regardless of how you get from state 1 to state 2. So that's basically one example of a state functional internal energy. And there are other examples as well, which we're going to see later on. So as indicated right here, the change in internal energy of a system is simply equal to the final energy value, final internal energy value, minus the initial internal energy value. All right. Okay. All right, let me just talk about the first law of thermodynamics, and then we're going to stop here for today. So the first law of thermodynamics is the same as the law of conservation of energy, which states that in any physical or chemical change, energy can be exchanged between a system and its surrounding, but no energy can be created or destroyed, right? That's the first law of thermodynamics. Now, we can mathematically represent this law by using the relationship between the internal energy of an object or system, the heat that is either absorbed or lost, and the work that is either done or on the system or by the system, all right? So the relationship between these three terms is given right here, right? And this is basically the mathematical expression for the first law of thermodynamics. Delta U is equal to, delta U of course is the change in internal energy, is equal to Q, which is the change in heat of the system, plus W, which is the work that is done on the system, all right? So that is the first law of thermodynamics, all right? Now, when using this law, you have to be careful about the sign conventions, right? And this will become important when you're reading questions and you have to interpret it correctly in order to use the correct signs for the different terms, right? So I'm going to go through these and hopefully I'll get to an example before time is up. Okay, so if energy is entering a system, right? That means that the system, as far as the system is concerned, the energy change is positive, right? Now, if heat is absorbed by the system, then Q is positive. If work is done on a system, then W is positive, all right? So here we're saying that if you have energy entering the system, then the energy must be positive from the system's point of view, right? And from the system's point of view, if heat is absorbed by the system, then from the system's point of view, the heat value will be positive. And if work is done on the system by the surroundings, again, from the system's point of view, the work will be positive, all right? Okay, then we look at a situation where energy is leaving a system, right? In which case, the change in energy as far as the system is concerned is negative. So if heat is given off by the system, Q is negative, and if work is done by the system, then work is negative, all right? So this diagram here basically summarizes what is stated above, right? So here we have the system, right? So as far as the system is concerned, if heat is absorbed by the system and work is done on the system, then the heat value and the W value will be positive. But if heat is lost by the system and work is done by the system on the surroundings, then the value of Q and W will be negative, all right? Okay, so, oh, I thought there was an example. There, okay, I'm gonna stop here for today. I don't think I need to start this topic and then stop in the middle of it prematurely. So basically that's it for today. Unless there are any questions you guys have. Any questions?
Not I.
Okay, so let me remind you of the test. If you have not, I can't imagine nobody downloading it and at least starting it, but if you have not downloaded it yet, it's due by tomorrow. So you need to jump on it and make sure it's done, all right? What's the other thing? Oh, for those of you who are members of the STEM Club, we'll be meeting on Monday at 12:30. You should be able to access the link through the STEM Club shell, but if not, what I'll do is I'll post the link online in Canvas so that you guys can have access to it and therefore make it to the meeting on Monday at 12:30, all right? And I think that's all I have by way of announcements. Before I forget, let me take roll. Let me go to Today is the 17th. Okay, let me stop sharing. Okay, so let's see who's here. Is Arias Rios here? Nope. Barber?
I'm here.
Okay.
I also had a question.
Okay, no problem. Let me just do this first. Cannon,
Yeah.
Chang, Chavis, Clark, DeGraff, Franklin, Han, Taron is here. Holland is here. Jurgensen is here. Reese, where's Reese? I don't see Reese. Rouse is here. Ronalds is here. Santiago is here. And Smith, I don't see Smith. Okay. So somebody had a question. Yes.
It was me. I was just wondering if you saw, I had emailed you about getting a Skype account. I was just wondering if you saw yet.
Let me see. What's your last name again?
Barber, B-A-R-B-E-R.
B-A-R-B-E-R. That's interesting. Let me look here. I can't seem to find it.
Okay.
So maybe you need to resend it. For some reason, I don't see it here.
Okay.
Hold on, wait a minute. Hold on. Wait a minute. Oh, I guess you signed on as Taylor B.
Oh, yes, that's it.
Okay, that means you're here. Yeah, I got
Okay.
you.
All right, thank you.
Yeah, no problem. Okay, any other questions? Any other questions?
Nope.
Nope. All right, so see you guys on Tuesday.
All right.
All right. See you then.
All right, take care.